Hello, everyone. My name is Fedor Sakharov, and I'm here to talk about the Ethereum and its smart contracts. So the agenda of my talk today is the following. First, I'll talk a bit about me, then a bit about Ethereum and how it works, and then we'll jump to smart contracts and their internals. And then I'll cover a bit how I implemented support in Redari 2 for Ethereum reverse engineering and debugging, and then a bit about the future work and what can be improved. So, about me. Those of you who develop Redari probably know me by my GitHub handles. It's Manteki or Manteki in lead on Twitter. I mostly write code in C or Golang or whatever system development stuff you may find. It's on networking. Xvilka brought me to Redari, I think, like 5 years ago, and mostly I've been implementing new architectures, embedded stuff, some Hitachi processors, stuff like that. But I made a living working in information security and since recently in crypto. And it's not a surprise that now I'm unemployed, so I've declared bankruptcy. So, now to Ethereum. I don't see you quite clearly because the light is so sharp, but I would really like if those of you who know what Ethereum is or those of you who have cash in Ether, raise your hands, please. All right, good. And probably some of you know how Ethereum smart contracts work. Okay, nice. So, what Ethereum really is, its definition from the Wikipedia, is a distributed blockchain-based computing platform and operating system featuring smart contract functionality. And it's interesting that most people perceive Ethereum to be exactly that. And yesterday at the restaurant, I've been talking to Xvilka, and that's exactly what he said. So, but in what actually Ethereum is, well, it's often referred to as a blockchain 2.0, or if you have ever installed MetaMask, they call it Web 3.0, all the hype. But actually what it is, it's a lot of peer-to-peer networking that exchanges transactions and events on the Ethereum network, and the Turing-complete virtual machine. Well, both of those parts are really interesting. I have researched a bit the VM, so now I am talking about that. But now I'm researching the peer-to-peer stuff. It's also quite interesting. You can probably take a look. And there's also some money inside. I think the total market cap for Ethereum right now is some $30 billion, something like that. And if you put those two things together, that makes the research of Ethereum quite interesting. There have been a lot of known hacks in the Ethereum ecosystem recently. Well, the most known and the most recent hack is the parity freeze, where a logic error in the multi-sig wallet has led to $400 million freezed on the Ethereum blockchain forever. Well, multi-sig wallet is also a smart contract, so it's probably interesting investigating that. Also, yeah, the multi-sig also led to $33 million stolen, and the DAO hack, which led to a hard fork in Ethereum. So you know there are now two Ethereums, Ethereum Classic and Ethereum, that also led to $70 million stolen. Okay, so what are smart contracts and how does their bytecode work? Smart contracts are intended to be a digitized version of real-world contracts. They are intended to simplify your life whenever you are, I don't know, buying something or doing complex legal transactions, like probably buying a car when you have to go to multiple government institutes to register it and to pay your taxes and so on. Or you're probably doing your job and you want your employer to pay you in a more transparent way. And Ethereum uses languages to describe the logic of those contracts, and different languages exist. And every one of them is translated to Ethereum bytecode, which runs in the Ethereum virtual machine. The runtime is the Ethereum virtual machine, and it's specified in the yellow paper by Vitalik Buterin, which is the official specification of Ethereum, its internals, its protocols, the way it works, the way the mining is happening, and so on and so forth. Well, actually, it's a stack-based machine. Probably it's very similar to Java in a way. When I implemented the Redari support for Ethereum, I took a lot from the code of Java, I think, because they're similar in being stack-based machines. The code is always run as intended, so multiple miners and anyone on the network can rerun any transaction that has happened before or is submitted to the network to verify it. So we always know the desired output if the virtual machine sticks to the specification. And the code will always terminate. That's an important thing, because a lot of people say that blockchain 2.0 differs from blockchain 1.0 because Ethereum and blockchains like it have Turing-complete smart contracts. Well, Turing completeness is not a bit true, because in any way you cannot run an infinite loop that will never terminate. Each execution of Ethereum transactions terminates in some time. Now let's take a look at the example. Solidity is one of the most widely used languages for creating smart contracts. It's basically a JavaScript-like language. It differs from JavaScript in the way that it has types and some Ethereum-specific keywords. But basically, it's the code like this, which has some functions which are called by transactions. It has no single entry point, and it's compiled and it's stored in the blockchain, which is a global distributed database available to anyone. So here is an example about how the ABI of the compiled contract works. We can ask the Solidity compiler to output the ABI for our contract for us. So it's actually a JSON file where each method in the contract is described with its parameters and its outputs, its name, and different properties which are Ethereum specific, like whether it is payable, or it doesn't mutate the state of the contract, or if it's constant, if it's a function or anything else, and so on. The contract itself is compiled to bytecode, also by the Solidity compiler. And basically what it is, it's string, well, hex-encoded bytecode. Well, that looks like that if you compile it by the compiler. It's just a hex string. And its execution will always start from the first byte. And as I've already pointed out, when the transaction is called, it has some input parameters which are encoded accordingly to the ABI. The most widely used IDE for Solidity contract is the Remix by the Ethereum Foundation. It's a web-based development environment that has all the things you need. It has the editor, compiler, and debugger, and even the embedded VM to run your code and test it. I'm talking about this because I want to kind of walk through contract creation to bytecode, and then from bytecode to reversing it, so you just understand what's going on. So here's our contract how it would look like on the Ethereum Remix debugging and IDE. So when you deploy it in the Ethereum Remix, it will look like that. You can use different VMs for testing. You can connect to the node on the main network. You can use the embedded JavaScript VM, but as soon as you deploy the contract, as you may see, there is a list of methods you can use to send transactions to it. So down at the bottom of the screen, there's the setA method, which takes a uint 2256 operand one. So you'll be calling that if you want to test your contract. And it also has, when the transaction is sent, it has a lot of stuff in it. It has the hashes, it has the input data, and it has different parameters, how much gas was spent when this transaction was executed. But we are particularly interested when reversing and debugging Ethereum contracts on the input field that's cropped here. I don't know why, but as you see, it's some hash-like value. So if we go to debugging, we can see it unfolded. What that is some string with hash-like 4 bytes in the beginning. And if we call our setA method with an argument of 42, 42 will be encoded in the end of the string. That's actually how the whole ABI encoding for calling smart contracts methods works. Now to the bytecode. Ethereum, as I've said, is stack-based machine. It's, I think, von Neumann because the memory and the stack and the storage are separated from the code memory. And during runtime, data is stored in memory or in the stack, and the permanent storage, which lives on blockchain and survives throughout different executions of the smart contracts method, well, it's the storage. So here's a simple example of how a stack-based machine works. You probably all know how that goes. Now, the flow control is done pretty conventionally. Well, all the jumps and all the calls inside the smart contract code are done with the jump instructions because call instructions, they perform quite a different task in Ethereum. And all the beginnings of the basic blocks begin with the jump dest instruction. That's basically a NOP, which marks the valid beginning of the basic block. So I presume it's some kind of control flow graph integrity thing. So if the virtual machine sees that the jump leads to some point where is no jump dest instruction, that's a violation. So I think that will terminate the execution. So as you see, here's an example, blah, 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 and at some point we push the address we want to jump to and jump to it, and at the address 0x2, it's the jump dest instruction, so here's our loop will be going on. So there are two types of instructions. The normal instructions you always find in a stack-based machine, which do arithmetics, control flow, whatever. And there are also Ethereum-specific instructions which load your data from the transaction inputs into the virtual machine address space, which call other transactions. For example, call and call, delegate call, they actually will be performing calls to other contracts on the chain. Revert will terminate your execution and return the funds to you in case of a failure. The suicide will drop your contract and kill it from the web. And that's one of the instructions that tries serious security concerns. I think it has been used to freeze the $400 million in the recent parity hack when some of the contract was suicided. And now let's take a look at how it looks in the Redare. The code always starts from the very beginning, from the 0 byte. The first instructions, they are the preamble, which is relatively the same for any smart contract. Well, what it does, it loads the data from the input into the memory of the virtual machine. and it does some initialization. Well, the first instructions, they initialize the memory. mstore initializes it, and call that data size returns the length of the input data we have been called with. And as you see, if it is less than 4, we jump to some location yet unknown. But if the input is longer than 4, then we continue our execution. Now, as I've said, this code will load the data into the memory. And now the interesting part is what happens next. We take our input string and we end it with the mask 0xFFFFF. And if you remember how the input looked in the Remix debugger, the first 4 bytes are some hash function. So what the code does is takes that 4 bytes hash from the from the input data. Now that hash is a signature of the method we are calling, and actually that's 4 bytes, the first 4 bytes of the, I don't know how do you pronounce this hash function, ketsec, but whatever. If you know, just tell me. Of the function signature. So if you compute this hash of the set A with 1 parameter unsigned int 2056 and take the 4 bytes, you will see that it equals those bytes we are comparing the first 4 bytes of our input in the code of the smart contracts. And well, if it is equal to what we want, we continue our execution as intended. But if not, if our contract has been called with some rubbish data or some hash that it doesn't know of, the execution terminates. There are also some other checks done before we start actually executing our method in the smart contract. They will be better seen on the next slides, where there's a CFG output from Redare. But at some point we arrive in the smart contract method that actually adds 42 to the input parameter and stores it into the permanent storage. So as you may see, it's quite clear from the code that that's exactly what happens. And in the end, the result is stored with store instruction to the smart contract storage. Now, Ethereum yellow paper is quite different from your regular data sheet on any controller you may find, or any processor, ARM, whatever. When you implement its disassembler or assembler or try to figure out what's going on, you'll be dealing with some information which looks like this. It has a lot of math in it, unlike your normal data sheets. Now, how I implemented the support for reversing these smart contracts in Redare. Well, the disassembly plugin is quite straightforward. The opcodes just 1 byte instructions that rarely take some arguments because the machine is stake-based. Actually, there has been some work done before me on those plugins, I guess, implemented by Pancake, but I just fixed the stuff in there, so it disassembles contracts correctly. So it's just you follow the yellow paper and try to understand things going on there, and you'll be good to go. So the analysis plugin is quite a bit tricky because we're dealing with a stack-based machine. So all jumps and all the operands are taken from the stack. So we have to somehow cleverly compute them to know the destination addresses. But quite often in Ethereum bytecode, the push instructions precede the jump instructions, so you can just take the operand from them and say that's your destination address. It doesn't work in every case because, as we will see further, there are examples where that's not true, but for, I think, 80% of calls and jumps, that's true. Now, how it worked as I implemented it in Redare, well, quite good. It's understandable what's going on. But the only thing that the drawback, as you may see, the Ethereum uses quite long operands. In fact, most of the time it operates on the 32-byte numbers. So there's the push 29 instruction that pushes a 29-byte operand to the stack. And obviously it's not displayed correctly. I have yet to find out how to display that correctly in Redare. So it's part of the future work. Now the control flow graph looks like this. Thankfully we have a nice resolution, so it's seen clearly what's going on. As I've said, the first basic block is finding out the length of the input data. The second basic block is the function dispatcher that will dispatch your calls to the further code in the contract based on the signature, the hash signature. And in any case, if the smart contract execution fails at any step at this point, we arrive in this small basic block which reverts the execution. But if not, if everything is successful, we go on. And at some point, we execute our methods and jump somewhere and stop the execution. Now to the interesting stuff, how to implement the I/O plugin, because it kind of, each and every contract lives on the chain and it doesn't necessarily live on your file system. So it would be a logical thing to ask the Ethereum itself to provide the code of the contract. It turns out that Go Ethereum and other implementations such as Parity and CPP Ethereum, they provide you with a set of RPC interfaces which do a lot of interesting stuff. For instance, you can call the Ethereum get code. Here's an example with curl that just returns you a JSON document with the whole bytecode of the contract if you ask with the hash address of that contract. So just bring the libcurl and JSON parser into the I/O plugin. That's why my plugins, they live in Redare 2 extras, because they add external dependencies. And now we can talk to the node using the I/O plugin of Redare. Now, example is here. If you are using that example is valid if you are using your local node. You connect to EVM ://localhost port and the address of your contract, and the Redare reads the contract code for you. It's quite handy. Well, if that's not the case, you may probably use publicly available Ethereum nodes, but I'm not sure if all of them expose the necessary interfaces. Now, the most interesting part is the debugging plugin. Ethereum Virtual Machine has no known to everyone interfaces like GDB-int or JTAG or whatsoever, and you cannot actually trace the live execution of a transaction like you do with the normal processes or your firmwares or whatever you're working with in normal life. But you actually can also call an procedure call which will return the trace of any transaction that has ever happened on the blockchain. It's called a debug trace transaction. And what it returns is a long trace of this transaction where each field is the complete dump of the state of the virtual machine during the execution of that instruction. So for the first instruction in our smart contract. The trace will be the following. It's a push instruction. The program counter is 0. The stack and the storage are empty at the time. The memory is not initialized, and that instruction cost you 3 gas. It had no errors, so basically you take this long document, and what you do in the Radar plugin, you read this whole document, you just implement the API for the main Radar code, which provides you with ability to set breakpoints, to stop or continue your execution, and so on, all the stuff that the debugging plugin does. But what actually it does, it's not the live trace, it's the just scrolling and to and forth through this large JSON trace. Now, onto the future work. I think that the nature of Ethereum virtual machine suggests that ECL might be very promising, since we can actually emulate anything to any point in the execution of smart contracts, since it will always terminate, and that's a definite fact. I think that my future work will definitely include implementing the compiler in this or that manner. I'm thinking about R2deck, but probably RedDeck, because, and why is it usable? Because some of the recent researchers show that probably around 70% of smart contracts in the Ethereum lack their source code, so we can just kind of decompile them if necessary. And one of the really needed stuff that has been asked by many people participating in CTFs, the Ethereum-based CTFs, is the support for 32-byte operands, because it's a serious issue for them. And I think that the better jump, call, and return destination address computation. Now, there are some useful links for you if you are interested, if my talk interested you in further researching the security of smart contracts and their internals. Now there's going on a great blog series by Zeppelin in their blog, but you can also read my posts about the implementations and the internals of Ethereum smart contracts at my Medium. For those of you who love CTFs, there's a really nice CTF called Ethernaut, also by Zeppelin Solutions. Right now it has around 19 Jeopardy-like tasks, and if you exploit all the vulnerabilities, you will probably be an expert on smart contract security. Also, the yellow paper, the ABI specification, and all the rest. So that's all for today. I would like to thank you. Thank for the Radar team and Pancake for this great conference. And I would really love to hear your questions. And the best question receives a beer. I think it's some honeydew. I don't know, organic. Please, questions. Okay, no one gets a beer. Thanks a lot.